So built-in functions. So these four are built-in functions in our assertions. Okay. So what does all this does? What does it mean? Okay. So $1 and you have to give your expression. Okay. So it means like it checks that the expression is 1 hot. In other words, only one bit of expression can be high on any given clock edge. So if you are writing an expression, so only one bit of that expression can be high on any given clock edge. Okay, so here it doesn't mean like either expression only you have to give. Here you can give a signal also. So if you want a check, if you want to check a signal, means basically assertions is like to checking signals only. So you can give the signal name itself. Okay, so it just checks if only one bit of expression can be high on any given clock edge. It means, let's say your signal is a vector, so only one bit of the expression can be high in a given clock edge and remaining all should be low. So for that purpose, you can use this $1 hot and $1 hot 0 of expression. So this like in this way you have to write. So it just checks the expression is 0. So in other words, like only one bit of expression can be high or none of the bits can be high on any of given clock's edge. It means like either only one bit can be high or each and every bit in that expression should be low. Okay, so that's what $1 hot 0 does. And dollar is unknown of expression, or if you are giving any signal also, what it does is like it checks if any bit of expression is X or Z. Okay, so if you want to know, like for suppose dollar is unknown of W data, for SRAM you are giving W data, you want to check whether W data is of 4-state type. So you can get values 0, 1, X and Z. You want to know whether X and Z values are generated for that signal. So if you want to know that, you can use this dollar is unknown of W data, the signal which you want to know, that signal if you give it. So it will check if any bit of expression is X or Z. Let's say you are having 32 bit. So in that 32 bit, we don't know like which bit will be X or which bit will be Z. So in order to know that, you can use this dollar is unknown. Okay. And dollar count once. So it just like if you're giving any expression, so what does it does is like it counts the number of bits that are high in a vector. So let's say 32-bit variable you have given here. So randomly you are generating value, 32-bit value you are generating for that variable. So in that 32-bit value, how many ones are there? If you want to know, you can use this dollar count once. Okay, so it will let you know that how many bits are high, means how many bits are 1 in a vector. Clear, everybody?
Yes, ma'am.
Okay. And you have some other sampled value functions. So what are those? We'll see. So as I told you, like $fell, we have seen in the previous example. I think in this, yeah, $fell. So what does this $fell and all does? So $sampled, if you are using $sampled, it means like it returns the sampled value of expression with respect to the last occurrence of clocking event. Okay. So last occurrence of clocking event, it returns the sample value of expression. $sampled of expression you have to give. For all these things, you have to give any expression or a signal also, you can send it. Okay. Whereas $rows of expression you can give or a signal. $rows of A, like suppose you were giving a signal. So what does it does is like $rows of A means from 0 to 1, it will change the signal. Okay. So returns true if least significant bit of expression changed to 1. Okay, so it returns true if you are using a vector signal. Okay, so if LSB of that signal is changing from 0 to 1, so then it will return true. If it is not changing, then it will return false. Okay, so similarly $fell, so it returns true if LSB of the expression is changing from 0, is changed to 0, means from 1 to 0 if it is changing. $fell means it was falling from 1 to 0. Rose means it was rising from 0 to 1. Okay, remember like that. So it returns true if the expression is least significant bit of expression is changed to 0, and otherwise it returns false. Dollar stable means it's like constant. Okay, returns true if value of expression did not change. So for a expression or for a particular signal you were using dollar stable, it means like it will be, the value will be stable until how many clock cycles you want it to be stable, that many clock cycles it will be stable. Okay, clear everybody? And we have dollar past construct also. So what does this dollar past is like? Dollar past means it will check for the previous clock cycle signals also. Okay, so whereas this can't be done in your by using immediate assertion, but by using concurrent assertions, in that by using dollar past construct you can check conditions in the previous clock cycles also. Okay, so if you are mentioning like dollar past of the signal name and number of clock cycles at a particular signal, before how many clock cycles, if you want to give any value you can assign it, or if you want to check also you can check it. So like this, if you mention, so it means like, what does it means like when your B is high? Okay, when your B is 1, this is called as implication operator, this one. Okay, I'll explain you in the next coming slides. This is called as implication operator. What does implication operator does is like, it will check if you're using implication operator in the same clock cycle. So it is similar to, let me, so this symbol is similar to double hash 0. Okay, because double hash 0 is also in the same clock cycle. This implication operator will also check by you in the same clock cycle only. Okay, so this is similar to this, and here you are checking signal A before 2 clock cycles, it should be like 1. Okay, so property checks that in the given positive clock edge, if B is high, then 2 clock cycles before that A was high. Okay, so if you're not giving equal to 1 also, if you're giving dollar past of 8, means like A is high before 2 clock cycles. Okay, you want to check this condition whether A is high or not. If A is high before the 2 clock cycles, then the property will pass. If A is not high, then the property will fail. Okay, so in this way you can also check a signal in the previous clock cycles also. Clear? Anybody having any doubts? So you can also use this dollar past construct with a clock gating signal. So this is called as a gating signal. So what does this like? What does this does is like? So in a given positive edge of a clock, so if B is high, then 2 cycles before that A was only high if gating signal C is valid on any given positive edge of the clock cycle. It means until your C is high, then only your A should be like A was high. If this is, if your C signal is not high, then if A is high also, your property will get failed. Okay, it will not pass. So this also you can use. So gating signal on a given clock edge, the gating signal has to be true even before checking for the consequent condition. So this should be high. Okay, before checking this condition in the positive edge of a clock only, this C signal should also be high. So this is called gating signal. Yeah, now we have come to the third layer in our assertions. Those are property. Our first layer is Boolean layer, and our second layer is sequence layer, and our third layer is property layer. So property layer is built on top of sequence layer. So it's like sequence are building properties, building blocks for properties. So it can use 0 or more sequence to check a design assumption. It can use any number of sequence. So 0 assertions because property layer can contain Boolean layer directly. So it can also contain Boolean layer. Okay. So a property declaration by itself does not produce any result. Result of a property, like in the case of a sequence, is either true or false. So property declaration itself does not give you any result. So how the sequence will evaluated, like either true or false, in the same way property will also get the result as true or false. True means it is passed, false means it's not passed. So these properties you can be declared inside a module, interface, program, clocking block, and package like sequence. Okay. So properties can have following kinds of sequence. So properties can have a sequence and negation, disjunction, conjunction, if else. If else also you can write inside a property. Implication, another named property. You can also property can also contain another named property also. Okay. So this is the syntax, property and end property. In this way you can write between the keywords. Okay. So forbidding property. So what does this means is like, you are writing a sequence, you're calling that sequence here by using not keyword. Okay. We are expecting the property to be false always. This is called forbidding property. The property is checking for a true condition. Property can also be forbidden from happening. So it means like we expect the property to be false always. So if property is true, the assertion fails. So this is called forbidding property. Okay, for forbidding property, what we were using is like, we'll be having a sequence. That sequence, they'll be like writing not keyword and the sequence name. So if you are writing like this, it is specified that this sequence will never be true. If it is never true, then obviously your property will not be true. If your sequence was failing, your property will also fail. So this is called as forbidding property. Okay. We have one more thing is like negation property. It's also same thing. Here you are not like, you are writing inside a property directly the not keyword. So by using this not keyword, this entire condition, if it is true also, you are making it as false. So when your condition is false inside a property, your property will also fail. That is called as negation property. Clear? Like what is a negation property? The difference between negation and forbidding property is like, only thing is, in the forbidding property, you are calling a sequence and making that sequence to be false. Whereas in the negation property, directly you're making the condition to be false. Okay, that's the only difference between forbidding property and negation property. Okay, and here another named property. Here you were written a property. This property you are calling it another property. So this is called, one property can call another property. So this is called as another named property. Clear up to here?
Ma'am, practically in which situation we'll be using this negation and forbidden property?
Practically, like let's say you were checking
Okay.
a particular condition whether it was true. Okay, so it was true, it was fine, but you want to check that whether your property or at positive edge of a clock, if that condition is false, whether your property is also becoming false or not. It might be
Okay.
that whether your property may also give you some differences, right?
Yes, ma'am.
It is also a tool specific. It's also like what we were writing. These assertions were written by us only. They'll only be writing it. So we don't know whether the changes like we are placing, it's like how I can say, see, inside an IC, we were placing all our components. So the environmental, like the surrounding environment, can also cause a particular thing in an IC to be fault as like to be act as faulty, right?
Yes, ma'am.
So those conditions we were just mimicking by writing our verification environment. We were not 100% taking that environment and we were mimicking. We were just mimicking only 70 to 80% of outer surrounding verification environment. So in that, if that was also failing, so then we can use this negation property and forbidding property. So it was, if it was working fine for these things also, we can say okay, this property was working fine in any conditions. But if it's not working properly, so there might be something faulty in our property only. So then again we
Yes.
write that one.
Okay. Okay, ma'am.
Clear?
Yes, ma'am.
Yeah. Now we came for implication operator. This implication operator you will be using only inside a property, but not inside a sequence. Okay. Remember, some operators you will be you can use only inside a property. Okay. Whereas the operators which you are using inside a sequence, those can also be used inside a property. Why? Because inside a property, a sequence can also be called. So all the sequence operators which were used in sequence can be used inside your properties also. But whereas the operators which are used inside a property can't be used inside a sequence, because inside a sequence you cannot call a property. So remember that thing. These operators which were used inside a property should be used inside a property only. Okay. It should not be used inside a sequence. If you are using it, it will throw you an error. Okay. So implication is equivalent to an if-then structure. So LHS of implication is like antecedent we call, and RHS we call it as consequent. So if antecedent succeeds, then the consequent is evaluated. Okay. So if your LHS side is true, then only your RHS side will get evaluated. If this is false, then your RHS side will not get evaluated. That's what implication operator does. Okay. So this construct can be used only with property definitions. So it cannot be used in sequences. And two types of implication operators we were having. So one is overlapped implication. Another one is non-overlapped implication. So it's like this one, like when I'm preparing my PPT, like I'll add the symbols clearly. Okay. So it was like, I'll just show you. So this is your implication operator, overlapped implication operator, and this is your non-overlapped implication operator. Okay, the difference between these two is like, if you are using overlapped implication operator, so it means like, if you are using like this, what does it say is like, if A is high, in the same clock cycle, B should also be high. So this represent, overlapped implication represent to check the condition in the same clock cycle. Whereas if you are using the same condition by using this non-overlapped implication operator, it means like, if A is high, in the next clock cycle, your B should be high. So this non-overlapped implication operator consists of one clock cycle delay. Okay. So let's say if you want to mention like your A should be high and your B should be high after one clock cycle. So after one clock cycle, either you can use this non-overlapped implication operator, or you can simply use when your A is high, after one clock cycle, your B should be high. This way also you can use, this way also you can use. Okay. And if you want to use like A should be high, so it means like overall after 3 clock cycles, this consists of 1 clock cycle and double hash 2 consists of 2. So 2 plus 1, 3. After 3 clock cycles, your B should be high. So this one, you can simply write it as like this also. In this way also you can write. Clear? What are overlapped implication and what are non-overlapped implication?
Ma'am, overlap means A and B both will be high.
In the same clock cycle. Overlapped
Oh,
implication means it will check in the same clock cycle. Whereas
oh,
non-overlapped, it will check in the next clock cycle. The RH,
okay.
it will be checked in the next clock cycle, whereas this in the overlapped implication, it will be checked in the same clock cycle.
Okay, ma'am.
Okay. So that is your implication operators, overlapped and non-overlapped. So yeah, so denoted by this symbol. So if there is a match on antecedent, then consequent expression is evaluated in the same clock cycle. Okay, in the same clock cycle. So this is like if A is high on given positive edge of clock, then signal B should also be high on the same clock edge. So that's what. So if you are mentioning like this, it means like A should be high in the same clock cycle. After 2 clock cycle delay, B should be high. So this expression, you can also write it in another way by using non-overlapped implication also. So how it is like if A is high, so here you're having 2 clock cycles delay, right? Instead of using overlapped implication, you can use non-overlapped implication operator, can give 1 clock cycle delay and can give like this. So both are same. Okay. This expression, and if you write like this also the same expression, both are same. Clear?
Yes, ma'am.
So this is overlapped implication. And the non-overlapped implication also I have explained you. So the symbol is this. So the consequent expression is evaluated in the next clock cycle, whereas overlap in the same clock cycle. So this is how you can use inside a property only. You can use this non-overlap implication. And we have a disable if construct. Okay. So this is a keyword. So disable if. So here you are disabling if reset. Your reset signal you are disabling. That too, when reset equal to 1, that value only you are disabling. Okay. So it means like you are disabling if reset is 1. But you are not disabling when reset is 0. Reset is 0 is still valid. Only you are disabling only for one value of a reset, that is 1. Okay. So if you see here, when your reset is high, you are disabling that one. Means you are not checking with the reset equal to high condition. So A is high in the same clock cycle. After 1 clock cycle delay, your B should be not continuously high for 3 times. After 1 clock cycle, your C should be high. So here, disable if of negation of reset. So here, if any reset is detected low at any point, the checker will stop. Okay. So here you are using, okay, they have used a different thing. It was not added. So generally, I'll explain you in general way. So yeah, see if you see this, disable if reset is high. Means when your reset is high, you are disabling it. So while executing this entire expression, if in any of the evaluation time, if your reset becomes from 0 to high, means from 0 to 1, if your reset becomes from 0 to 1, this property will fail. Means it will stop. Okay. So in order to avoid that, you are just checking only for reset equal to 0 condition only, not for reset equal to 1. So when you use this disable if construct, if your reset becomes 1 also, it will disable it, so that your property will not get failed. Clear? Okay. Um. See, in the starting of the assertion concept only, I have said like you have a reset signal. So initially it should be high. After 10 nanoseconds, it should be zero. Okay. So we don't know whether again it might go up or not, right? So again, when it goes up, if like, let's say, so if reset is high, your output should be zero. Else means when your reset is zero, you are assigning output some value. Okay, this is like a D flip flop, you just consider. Okay, so initially like reset, you are writing a condition like reset should be high in your test bench. After 10 nanoseconds, reset should be high, and after 10 nanoseconds your reset should be low, right? So now you want to check this condition. Okay, so now you want to check this like what is the value of your y based upon your reset value only. So reset, like initially up to 10 nanoseconds only your reset is high. After that, till until your end of your simulation, your reset will be zero, means it should be zero only. Again, if your reset becomes 1, your output will become 0, right? According to the condition.
Yes, ma'am.
Right, so now you are checking a signal. Okay, now let's say you are writing an assertion to check a signal, like you are just checking this b value or you are just checking the y signal. Okay, so when you are checking this y signal, so if again reset suddenly goes high, your y again will become 0. So in order to avoid that, you want to just check continuously y signal whether it was getting any value or not from the D. So if you want to check that condition, you can use disable if construct. Okay. So disable if of when your reset is high. You are writing like this. It means after that you are writing some expression. Okay. So let's say like you are okay, just like this only. Okay, I have written. So this is some expression. So it means while evaluating this entire expression, if your reset goes high also, it will not affect the entire expression. Means it will not affect, it will not immediately go y as 0. Okay, because here you have mentioned disable if. So when your reset becomes high also, it was disabling the reset when it is high. So your output will not affect by that. You can check easily, means you can check the or you can monitor the y value continuously even if your reset becomes high also by using this disable if construct. Now clear everybody?
Yes, ma'am.
For that purpose you are using this disable if. Okay, so even if a particular signal is high in the middle of your evaluating of your property, it will not affect the property to be disturbed. Okay, so by using this disable if construct, you can make that signal disable even if it becomes high in the middle of evaluation of your property. It won't affect the property to be failed. It will always pass the property. Okay, for that purpose you can use this disable if construct. And we were having some more things like dollar assert on. So these are like global control on assertions at module or instance level. So dollar assert on, like constraint mode we were having, right? Constraint mode, random mode we were having. So similar way we were having assert on, assert off, assert kill. Okay. So it is default assert on is. So it's called assert on means all your assertions are on. Okay, so this it was like by default every assertion will be on only. So if you're calling this, it means that you have already called $assert_off or $assert_kill. After this only again you can call this $assert_on to restart your assertions. Okay, what does $assert_off is like? It temporarily turns off all executing assertions. If you're using $assert_off, so it will temporarily turns off the current executing assertions. Okay, $assert_kill means kills all currently executing assertions. At present time, one assertion was executing, that assertion will be killed if you're using $assert_kill. Okay, so these are some of the functions which can be used to control your assertions. Okay, and yeah, so we have a bind keyword. It means like we'll be writing our assertions in a separate module, like in a separate file. So how to combine that file, like how to add that file into your design. So in order to add that file, you can use this bind keyword. Okay, so when RTL is already written and it becomes responsibility of a verification engineer to add assertion, so we will only write assertion. So RTL designer does not want verification engineer to modify his RTL for the sake of adding assertion. So if we want to add assertion, because we were writing assertions not for the environment, only for the main signals of our RTL code, right? So if we want to add that assertion, so the RTL designer doesn't want verification engineer to modify his code, RTL code. So in that case, we can use this bind feature. Okay. So one can write all assertion to write in a separate file, and using bind the ports of his assertion file with the signals of RTL in his test bench code. Okay. So this bind feature can be used in module or interface. So this is your separate assertion file. So module, your assertion name, all the signals what you want to, like main RTL signals, inputs and outputs you are declaring here, and you are writing everything and you are ending this module. Okay, so this file you want to bind it. Okay, so how you are binding? So this is your DUT file. Okay, so this is your DUT file and this is your assertion file. Now by using bind keyword, okay, so in the top module or in your test bench module, by using bind keyword, your DUT name, DUT module name, and your assertion module name. Okay, and here the instantiation, obviously like TT, or I have said V code. So here you can use your name also, that name, and instantiating. Now we are instantiating by using named association. Okay, so here first you are writing your assertion signal, then in the bracket you are mentioning your DUT signals, and you are ending this module. So this bind you can use in either test bench or in the top module also. This is the bind keyword. Okay. This is one way to add assertion files to your environment. Another way is like, I'll just show you. Okay, so this is my assertion file for asynchronous FIFO. So if you observe previously in the example, so here I have mentioned all my IO ports of my RTL signal. So you can do either that one also, or simply if you want, you can just write, because all your main signals you have listed in your interface, right? You can simply call your interface here. This is my interface name and the interface handle. Okay, so in this way you need not to write all your IO signals, main signals. Okay, so simply you can call your interface name and your interface handle. But when you want to access like W clock, write reset, so all the signal you want to access with the help of interface handle only. Like how you are writing your DUT by using interface handle A dot or INTF dot, like that. Okay, so you have to use like this. So in this you can write it. Your assertion.
Ma'am,
Yes.
Ma'am, I cannot see the screen of particular the example which you are saying now.
Okay, okay. Now, now can you able to see my screen?
Yes, ma'am.
So here, instead of writing all our signals, we have already mentioned all our signals in our interface. So we can simply call our interface name and the interface handle. And by using interface handle, we can access all the interface signals like this, like how you are accessing in your DUT. So in the same way, you can write your assertions also by using those signals by accessing with the interface variable a dot write clock, a dot write reset. So for each and every signal, you have to use this interface handle a dot. Okay. So in this way, you will be writing your assertion file, and in the top module, you will just include your assertion file. That's it. And here top module, like you will be generating your clock, you will be generating your reset, and after that you will be writing your interface, next your DUT, and this is like different test benches I have written, ignore these things, test bench, and finally your assertion name. AS is the instantiation name, and inside our assertion what we have passed, interface variable, like interface handle we have passed, that handle you can pass it here and you can end module. Either you can add your assertion file by using bind keyword, or you can add this by using in this way also. Okay, by using interface also you can add your assertion file to your environment. Clear everybody? Anybody having any doubts?
Clear, ma'am.
So all these assertions I have written by observing the output waveform of my asynchronous file. Okay. I think I'll just share a new meeting ID. Just come there. I'll explain you, like by observing the waveform, how you can analyze those signals and how you can write assertions. Okay. I'll just explain you orally. And in the afternoon, I'll just cover the coverages part. Okay.